A very good morning, everyone. It's my great honor to welcome you all to our third day of webinar on transport phenomena in industrial processes, TPIP 2020. For the first technical session, I take this privilege to invite Professor Dr. Vidyavati Sadangi sir to deliver his talk. Dr. Vidyavati Sadangi, formerly Professor of Metallurgical and Materials Engineering Department, IGIT Sarang. Also, he was the head of Training and Placement Cell of IGIT Sarang. He has more than 40 international publications. Also, he has vast research experience at IMMT Bhubaneswar and technical experience at OSIL R&D head Rajgangpur. He had guided about 10 PhD scholars and still ongoing. So I request Professor Dr. Vidyavati Sadangi sir to deliver his talk. Please, sir.
Very good morning to all of you. Am I audible?
Yes, sir.
Many thanks to the coordinator to giving me a chance to speak something about the transport phenomena. Very cunningly, they have selected this topic because entire process metallurgy cannot live without transport phenomena, that is mass transfer and heat transfer. So it becomes very difficult in my part to cover this topic in such a short interval. So I decided what's best possible. In segment wise, I'll try to contribute something. Let us start. The general topic is mass transfer in metallurgy. So here, I thought that it should be divided into 4 segments. In segment 1, mass transfer process and metallurgical kinetics. In segment 2, convection and mass transfer in fluids. And segment 3, mass transfer between solid and fluid. And segment 4, mass transfer between 2 fluids, which probably will cover the topic up to great extent. In metallurgy generally, thermodynamics can predict whether a reaction is feasible or not in a given set of conditions. It can also predict the composition of the phase coexistence under certain pressure and temperature. At high temperature, such as extraction and refining of metals, the reaction rates are sometimes very fast, so that it becomes difficult to predict the kinetics. Examples: oxidation of alloying elements during steelmaking, metallothermic reduction of transition metal oxides. However, most of the reactions are not carried out near equilibrium. That is the reason a knowledge of reaction rates, that is kinetics, is required in order to analyze the situation. Since thermodynamics predicts about the end states, its conclusions are independent of the path the process follows and are therefore precise. This is not true in the case of kinetics. The kinetics is path dependent. The rate of the reaction process depends on the path it takes in going from initial to final stage. Again, what path the reaction will follow depends on a number of details as well as properties of the system, that is structure sensitive. Therefore, kinetic predictions are mostly are either qualitative or quantitative in nature, however, with some uncertainties. Now let us come to first segment, that is mass transfer process and metallurgical kinetics. Generally, all metallurgical systems of importance consist of more than one phase and are therefore heterogeneous in nature. The purpose of processes is to carry out the desired reactions amongst the various phases. Therefore, primarily, we are concerned with heterogeneous chemical reactions. Heterogeneity is a characteristic of technical processes. Kinetic stage. Let us, for the time being, consider 2 components A and B. combine together to give product AB. That's age in that. They are in two phases, phase 1 and phase 2. Component A belongs to phase 1, B belongs to phase 2. After combination, product AB, which also belongs to phase 1. So reaction 2, A1, B2, AB, 1. Here we can note that A doesn't dissolve in phase 2 because it belongs to phase 1. Similarly, B doesn't dissolves in phase 1 because it belongs to phase 2. Their only possible meeting place is the interface, dividing the two phases. Therefore, it is necessary to transfer atoms of component A to the interface, transfer atoms of component B to the interface. They combine together, there is a meeting time, they react together to form product A, which transported away from the interface. This is the most important for the transport phenomena about the process to the concern, because at the interface, most of the reactions are taking place. Once reaction taking place at the interface, existence of three things are there. Some of the component of A, some of the atoms of B, and product AB. So time to time, the reaction is to be carried out. In that case, time to time, product concentration at the interface should be removed. For time to time, AB should be taken out. Otherwise, reaction area will gradually sink and reaction will retard. In that case, reaction would come to state due to accumulation of more product. Each of these individual processes are called kinetic states. So those are transfer of A from the buck of the phase 1 to the interface, transfer of B from the buck of the phase 2 to the interface, chemical reaction at the interface, and transfer of product AB away from the interface into the buck of the phase 1. These processes can be grouped into two categories, step 1, 2, and 4, which are essentially mass transfer processes. And step 3 is a chemical reaction. Therefore, to have a proper understanding of metallurgical kinetics requires knowledge of both mass transfer as well as chemical kinetics. The formation of new phases takes place by process known as nucleation and growth, which are based on mass transfer and chemical kinetics. Am I audible? Hello?
Yes, sir. Yes, sir.
Okay. Now, for the above reaction, rate control steps. The kinetic steps summarized for reaction 2 are in series. They are a peculiar thing, see, are in series. Because if any one of them is prevented, the overall reaction would not have any one. That is, transport of atoms of A to the interface, transport of atoms of B to the interface, reaction at the interface, and product, a transport of product from the interface to buck of the phase 1. Out of these three, if any one stop, entire reaction stop. The action is analogous to switch off an electric circuit. The continuous analogy we may conceive the overall process is a series circuit, but the individual kinetic states are represented by resistance. If the resistance of a step is large, then it is considered to be a slow one, just as the magnitude of electric flows through a series of circuits is primarily determined by the largest resistor. Similarly, slowest kinetic state influence the overall rate most primarily determines the latter. Therefore, the slowest kinetic state is called generally rate controlling states, sometimes rate limiting states in all the processes, what the process may be. The conclusions would just be the reverse if these states are in parallel, because there are faster states, that is the one with minimum resistance will influence the overall rate most. However, It is never possible to conceive of a process where all the steps would be parallel. It would be a series parallel combination, and invariably, among these, the slowest step in series would be the rate control step. Let us take examples of series parallel combination. Sulfur reaction in blast furnaces, which essentially need reducing atmosphere. In this process, the basic reaction is sulfur, which is a liquid ion, oxygen in slag, sulfur in the atomic form, oxygen in the ionic form, combined together. Sulfur in the ionic form pass to the slag, oxygen in the metallic form or atomic form comes to the liquid metal. In order to allow the reaction to proceed, oxygen should be allowed to accumulate in the liquid ion. It gets removed. Now see, if more amount of oxygen getting accumulated in the liquid ion, what about its fate? What about the fate of the quality of the product? In that case, in the liquid iron, not only the iron, except iron, some other elements are also there, and temperature is quite high. In that case, affinity towards the elements except iron in the liquid iron is more towards oxygen. It gets removed by the reaction with other solutes in the liquid iron. Just like you see, manganese liquid iron oxidized with manganese oxides and passed to slave. Silicon combines with oxygen, forms SiO2, passes to slave. Carbon combines with oxygen, forms carbon monoxide, and passes to slave. All these reactions, 4, 5, and 6, are in parallel, but the individual states in them, as well as the kinetic states of equation 3, are in series. So that is supposed to be rate controlling. Now, let us come to convection and mass transfer in fluids. Convection and mass transfer in fluids. In fluids, both convection and diffusion contributes to mass transfer. Convection means flow of fluid. Sometimes it is obvious, such as a fluid flow through a pipe. Again, elsewhere, it may not be so visible, such as upward movement during heating of water or warm water. Nature of fluid. Convection is either free or forced convection. In free convection, flow is not caused by any external agent, but is a result of non-interaction between the elements. Let's imagine hot fluid element in a cold surrounding. The former would tend to move upwards as a consequence of buoyancy effect. Similarly, if the composition of fluid elements differs from that of the surrounding, the density would also differ. In case it is lighter compared to surrounding, it will move power. Mass transfer requires a gradient in concentration, and hence can itself being about free convection. Now, whenever you are coming to forced convection, it's said to be present when an external agent such as fan, stirrer, or pump induces the fluid motion. In forced convection, the magnitude of flow is much higher compared to that of free convection. Fluid flow, whether it is forced or free, falls under any one of the following three types: laminar, turbulent, and translation. In case of laminar flow, it is observed at low fluid velocities. It is characterized by a stable streamline. The steady laminar flow can be visualized in the following way. Inject a dye at a point in water. Under laminar flow, the dye would travel along a line straight or curved, which will be fixed like a static colored thread independent of time. This is a streamline. Now, if velocity of the flow is increased gradually, a stage would come when the streamline will start oscillating to and fro. This is translation flow. At a high velocity, the dye, as soon as injected into water, would get mixed up with water, and we end up with a colored water only. That is turbulent flow. The turbulent mixing is very fast flux, and streamline, the slowest rate in between translation flow is there. Now, for the time, see an example here given here. Figure 1 shows how velocity at point x0, y0, z0 in fluid varies with time. In the case of laminar flow, the velocity doesn't exhibit any periodic fluctuations. Whereas in the case of turbulent flow, fluctuations are there. At steady state, turbulent flow, the time average or smooth velocity is independent of time, but not instantaneous velocity. Sandeep, audible? Hello?
Yes, sir. You are audible.
Yes, sir.
Thank you. In the area of convective mass transfer, the nature of fluid motion plays a crucial role and hence to be ascertained first. Turbulent flow enables rapid mixing and mass transfer and hence is preferred for most of the engineering operations because in a stipulated time, good quality as well as quantity of product is required for any process metallurgy, any process. So it must be turbulent type of mass transfer. However, it is complex in nature from the viewpoint of understanding and theoretical consideration. Hence, convective mass transfer under laminar flow shall be taken first. The flow becomes steady in a short period of time, in general a mass transfer system, and therefore mass transfer may be steady state or unsteady state one. This bit consists of calculation, mathematical calculation. You can note it down, doesn't matter. Mass transfer under laminar flow is free convection. The flux Jx equals CIVx equals Jx difference plus Jix convection. Here, then this term is for diffusive flux. This is for convective flux. Here, Vix velocity of ith faces in the x direction x or across a stationary plane. Now, Jix convection equals Ci Vx bar, where Vx bar is summation of concentration of Ci Vix divided by Cix, which is equal to flux J by concentration, total flux by total concentration. As is the convection velocity along x direction. This is the average bulk velocity of the fluid as a whole. Combining previous equation 1, 2, and 3, which we have discussed earlier, this total Jix equals Jx difference plus Jx Ci summation all the flux summation all the flux. Summing up this equation for all the spaces in the fluid, ultimately summation Jix of the ith phases, Jx difference ith phases plus concentration of all the ith phases into Jx by summation of Jx. Or this terminology Jx difference equal to 0 or summation of ith phases di dci, rate of change of concentration with respect to the distance, that is coming to 0. For a binary system consisting, let's consider two components for a binary system A and B. In that case, this expression can be written as dA dc ca dx, dB dc dx, noting that d dot ca by dx is equal to minus dcb. In that case, sometimes some are coming negative. What is negative term is there? As process or reaction proceeds, concentration of the reactant gradually decreases. That's why generally sometimes it comes to negative. Now dA as a whole equal dB equal dAB in the case of equilibrium. So dAB means that it is common interdiffusion coefficient of the system AB as a whole. For a multi-component mixture, the meaning of DI is not that much clear-cut. It is to mention here that equation 1 is applicable to mass transfer across a plane which is fixed in location. Now, if we allow this plane to move along x direction, with the velocity Vx bar along with the fluid, then in that case, flux will be Jix, Jx different. Note here. Only steady state mass transfer will be dealt with here. Now, let's consider situation where graphite oxidizes with oxygen to give carbon dioxide. You see, we have consider the depicted figure 2, where a graphite block is situated at the end of the refractory tube. It is undergoing oxidation through the reaction C plus O equals CO2. At a steady state, on any plane, the molar fluxes of oxygen and carbon dioxide are equal and opposite. You see, molar fluxes of oxygen and carbon dioxide are equal and equal. That means in that case, what happens? The number of molecules of the reactants, gaseous reactants, is equal to number of molecules of the products. That's why at steady state, on any plane, the molar flux of oxygen and carbon dioxide product flux are equal and opposite. At steady state on any plane, the molar fluxes of oxygen and carbon dioxide are equal and opposite. So this can be written in this equation, Jixi equal to JO2, JCO2. From equation 3, Vix equal to 0. Hence, this equation again reduces to like this. Very long equation is there, you can write it down. Such situations, for generally you see equimolecular number of molecules of the reactants, gaseous molecules is equal to number of gaseous product molecules. That means that case, such situation when arises, this is known as equimolecular counter diffusion. Equimolecular counter C plus O2 equals CO2. Once we're discussing the reverse reaction, the CO2 may decompose to C plus carbon dioxide. It may decompose C plus carbon dioxide because in blast processes, what happens generally, when this reaction is taking place, that particular CO2 is not very much stable, but ultimately good amount of carbon is there. So CO2 again sometimes reacts with carbon to get to a CO. Again, sometimes that particular CO is not stable. Again, the diffusion, that particular carbon monoxide again dissociates to carbon dioxide and free carbon. That particular free carbon sometimes deposited in the iron lattice. So excess amount of carbon is found. Now mass transfer under the laminar flow. That is previously we have discussed about free convection. Now we are coming to forced convection. In case of free convection, the convection is caused by mass transfer process itself. But consider a situation where the fluid is flowing independent of mass transfer processes. That is forced convection. And the flow is laminar. A typical example is measurement of activity in liquid alloy by the vapor pressure technique, employing a carrier gas. That is in figure 3 given here. The activity of a species R in a solution is related to vapor pressure. Activity, vapor pressure, standard vapor pressure. The liquid here sometimes thermodynamics comes. The liquid alloy containing one volatile component is kept in a bottle. The inert gas, either argon or pure nitrogen, is passed over it at a known steady flow rate. The metal vapor, Me, escapes with argon and gets condensed outside the furnace. The partial pressure of the metal vapor, PME, is calculated by PME by P equal to NME, NRME. Here generally, P the total pressure, NME equal to NO, number of moles of metal deposited at the exit of furnace, and NR, number of moles of argon passed per unit time. Usually, number of moles of argon passed is very, very large compared to the number of metals deposited. So in that case, reaction changes to PME by P near about equal to NME by NR is equal to N dot ME by R, where N dot refers to rate in moles per unit time. Sandeep, it is audible?
Yes, sir.
Hello.
Yes, sir. You are
Or
audible.
dodgy? Or you are dozing? Because something boring is there, isn't it?
No, no, sir.
But N dot refers to rate in moles per unit time. Now, if PME, partial pressure of metal vaporized, is really the equilibrium vapor pressure, then it should be independent of flow rate. A typical plot of PME versus flow rate is shown in figure 4. The value in this plateau region You see, value in this particular creative region here. Accepted as equilibrium vapor pressure, which is almost straight, and higher flow rate. Depletion of vapor concentration at the surface of the liquid alloys lead to lowering vapor pressure PME. But the rise in the value of PME at low flow rate, you see, flow rate is low here. Definitely. In arriving at the above two equations, only conductive masses of metal vapor can be considered and diffusion can be ignored. In this particular figure, however, it is conceivable that diffusion will occur between the bore and the condenser as a result of concentration gradient from the higher concentration to lower concentration. So we can ignore it only if V bar x concentration metal is very greater than minus d dcm dx. V bar x is the convection velocity along x direction. But this assumption is not expected to vary to very low rate. Now, we are coming mass transfer turbulent flow. As figure 1 depicts on the very first one, figure 1, you see this is the figure 1. Steady state velocity at a point of fluid in turbulent flow exhibits periodic fluctuation of random nature in both direction and magnitude. Velocity of a fluid element at any instant may be different from that of its surrounding. This makes the element change its position with respect to its surrounding and go to a new position. New fluid element comes and fills this particular void mechanism, diffusion, void left first found. From the point of view of continuity, in effect, there has to be an exchange of two fluids elements as shown in scale C. Generally, that is packet of element A or first element passes to position 2 and fill this particular gap from this particular C2 again input leaves. This particular process continues till a homogeneous state is achieved. Elements 1 jumps to position 2 and elements 2 in action jumps back to position 1. Since these actions look like an eddy flow, the exchanging fluid elements are called eddy packets or eddy elements or simply eddies. Now, if there is a different concentration between point 1 and point 2, such actions of eddy would lead to net mass transfer from higher to lower concentration. This is known as eddy diffusion. What is eddy? Eddy flow. Fluid current whose flow direction differs from that of the general flow. The motion of the whole fluid is the net result of the movement of eddies that compose such packet. Molecular diffusion occurs because of random motion of atoms and molecules. Proportional to minus dc by d. Minus dc by d. dc by rate of change of concentration with respect to distance. Minus means as process passes, concentration of the reactant generally decreases. So whenever it will be expressed in terms of product, that should plus dc. Movement of AD is also just as random, and therefore rate of mass transfer by AD diffusion may be expressed by following equation: GIX bar ED DCI bar dx, where ED is a constant of proportionality and called AD diffusivity. Diffusivity, the total flux of spaces I in turbulent flow is given as sorry, JIX bar equal to minus D DCI dx plus CI bar dot VI bar x minus ED DCI bar dx. For first factor, this one is the diffusion, second one is due to convection, and third one is due to AD diffusion. In turbulent flow, every property we are concerned will show random periodic fluctuations. deal with time smooth parameter far above the quantities may be omitted. So ultimately the above equation changes to like this. When ED is very large compared to D because a fluid element contains billions of molecules and its jump distance is much larger than atomic distance. Of course, jump frequency is much less. Even then, on the whole, ED is very greater than D. Sarut and his co-workers have measured ED for hydrogen carbon monoxide in air and H2O in helium and CO2 and air, and obtained value of the order 100 times. Later on, they reported that it is much more than that, larger compared to the corresponding value of D. ED diffusivity depends on extent of turbulence. Higher value of ED leads to rapid mass transfer and mixing and turbulent and therefore of interest for many engineering applications. Example, mixings in open hearth steel making processes. A typical study of metal mixing in open hearth processes has been performed by different workers. In this particular study, we put a gold tracer at the center of the furnace and then measured the radiation intensity as a function of time and the charging dose. For this investigation, he has taken the assumptions. Assumption 1, only AD diffusion is important. Second one, diffusion is unidirectional along the effective path length in a restricted manner, effective path length in a restricted medium. Assumption 3, there is no non-uniformity in the vertical direction. And assumption 4, side walls do not have any influence. Out of these 4 assumptions, first 3 have some significance. But fourth one, he told that no influence. Out of the above 4, assumption 1 is justified. Because stirring is by carbon bubble. Carbon boiling might afford in steel making processes. Therefore, there cannot be any net convection in any horizontal direction. Also, molecular diffusion is quite slow compared to eddy diffusion. Assumption 2 is an approximation only. Assumption 3 is expected to be right. Whenever you are coming to assumption 4, doesn't appear to justify. To side wall, generally, let us put the time and debate from this side. You might have heard the rotary keel. When keel is rotating, you cannot avoid the side wall, effect of side wall. First of time, suppose keel is starting. In that case, from the bed, wall will absorb very good amount of heat. The time will retard. Obviously, other part will absorb the heat, and absorbed heat of the first part will transmit to the bed. In that case, then a heat transfer takes place. So obviously, side walls, whether it is static bed, or it is a fluidized bed, or it is a rotary kiln, plays a very vital role. So assumption side wall generally not appears to be justified. Since it is a case of unsteady AD diffusion, ED d square CB dx square equal to dc by dt, where generally I expresses is smaller than, greater than equal to x, which is greater than equal to minus 1. That is in between the two limits plus I and minus 1, plus 1 and minus 1. For generally, I stands for the half length of the bar of molten metal. C refers to the concentration. Gold tracer, which is proportional to the radiation intensity. C refers to concentration of gold tracer, which is proportional to the radiation intensity. Noting that typical value of D in molten iron is of the order 10 to the power minus 5 centimeters per second. It is seen that ED by D is of the order 10 to the power 7. So if one will depends on molecular diffusion of mixing, then he has to wait for the airs together. The source of stirring, come turbulence, is evolution of carbon monoxide bubbles. This study simply point out importance of stirring. So stirring effect, you can say, to better the but to obtain homogeneity at a faster rate. And mass transfer. Now we are coming to third segments. Mass transfer between a solid and a fluid. Now first two, you see, good number of applications in the first two applications, first two segments, a very good number of applications are there in different metallurgical processes. Those processes may be iron making, maybe steel making, maybe carbonization, maybe calcination, maybe you can say corrosion. In each and every case, there is mass transfer is a must. Without mass transfer, not possible. Let us, for the time being, let us take the example of carbonization process, formation of coke. Is there not mass transfer? It is mass transfer. Something, you see, once we're heating the particular coal, either in nitrogen atmosphere or inert atmosphere or in vacuum, what are we doing it? If it is inert atmosphere, we are heating it. The role of inert atmosphere not to allow the oxidizing atmosphere into the system. That's all only. But once you're providing heat from the lattice of this particular coal, organic matters, generally volatile matters, you say, escapes out. Escaping, leaving the place. There is a mass transfer, it is some mass. Suppose we are taking X gram of coal. After carbonization, take it out. It will not be X gram, less than X gram. That means in that case, if it is Y gram, X minus 1 escapes out. Escaping tendency, that escape out, that is mass transfer from the system to the outside. Now we are coming to the coke is there. Combustion of coke you are taking. Is it not a mass transfer? It is a mass transfer. Maybe process may be different. Maybe diffusion. You see, coke become porous now. We are allowing it to burn or allowing it to combine with the carbon, with the oxygen, or other oxidizing atmosphere, maybe CO2. In that case, what happens? The porosity available on the surface or internal geometry of the coke, the oxidizing gases O2 and CO2. Once they're entering, there is a mass transfer, oxygen is some temperature is high. This combining with the carbon of this particular periphery present in the coke. And ultimately, O2 in combines together to form CO2 and CO2 out. Mass transfer, 32 in, 44 out. And whatever the system it may be, in process metallurgy, in purification, in or steel making process, mass transfer is must. Now does come mass transfer between solid and fluid. Solid and fluid. Fluid may be a gas, fluid may be a liquid. In that case, earlier discussions were concerned with the process of mass transfer, the bulk of the fluid phase. However, in most of the industrial operation, turbulence prevents leading to a rapid mixing in the fluid bulk. This is true in most of laboratory applications as well. There ought to be logical concern with mass transfer amongst phases, at least one of which is fluid. In view of the fact that mixing in a bulk is fast, the mass transfer processes, the phase boundary offer often rate limiting in chemical metallurgical reactions. Mass transfer processes at the phase boundary are often rate limiting in chemical metallurgical reactions. Let us take the example of reduction of iron ore. Iron ore is solid, fluid is carbon monoxide. Similarly, oxidation of metals. Metal is solid, oxygen is fluid. Let us first look at a solid fluid interface. We shall restrict ourselves to the fluid side of interface only, because in the solid side of the interface, laws of diffusion may be applied in a straightforward fashion is required. Boundary layer mass transfer coefficient. The flux is given in general by the equation Jix equal to minus d dci by dx plus ci v bar x minus ed dci dx. When putting x equal to 0, it covers about 0 distance at the coordinates of the solid fluid interface and omitting the suspect I because it is redundant, the above equation, and it takes the forms like this, x equal to 0. Now, velocity boundary layer. It is expected that layer of the fluid just at the solid fluid interface slip past the solid, since this would require an unduly slip past the solid, since this would require a little large air stress, which a fluid is unable to sustain. Therefore, the relative velocity of the fluid with respect to the solid is 0 at the interface. At the distance from the interface in the bulk of the fluid, the relative velocity has a value. This gives rise to a velocity gradient in the fluid layer adjacent to the solid. This layer is velocity boundary layer. This layer is known as velocity boundary layer. Since the velocity approaches the work value in an asymptotic manner, the thickness of the velocity boundary layer, del V, will mathematically tend to infinity. At distance, the velocity boundary layer can visualize demonstrated in high viscosity liquid, like in glycerol. This thickness is of the order of a very millimeter, of a millimeter or less than liquids, or less for the liquids, and a centimeter or so in for gases. And the value depends on the nature of the fluid flow, etc. Since the velocity is small near the interface, laminar flow prevails there, even though buck flow may be turbulent. This laminar flow is a laminar sublayer. This is known as laminar sublayer. It is separated from the main flow, if it is turbulent, by a transition or buffer layer. If laminar flow prevails over the majority of the boundary layer, the latter is called laminar boundary layer. Because of the mass transfer, the concentration gradient of the transferring species I also develop near the solid fluid interface, which is generally shown in figure 2. You see, this is figure 2 I'm coming. Figure 2 illustrate this. There are also concentration changes asymptotically to the bulk value. This layer where the concentration gradient is present is termed as concentration boundary layer. Without the concentration gradient, mass transfer is not possible generally. This thickness of such layer will be del C. This is more or less with calculations are there. Generally, let us examine the mass transfer situation at the interface of x equal 0. It is to be noted that v bar x at x equal 0 and edx equal 0 because this is from laminar flow. When jx equal to 0 equal to negative del dc by dx dx, assuming d is to be constant, jx x0 is equal to minus d dc by dx x equal to 0. This is equal to d cs c0 by d. But generally, cs c0 stands for concentration at the interface and concentration in the bulk of the fluid. As shown in the figure, delta has been obtained for figure 2. This is the figure 1, this is figure 2. Yes. As shown in figure 2, del x has been obtained by constructing a tangent to the concentration distance at x equal to 0. So the value of d obtained this way is related to the mass transfer flux. It is known as effective concentration boundary layer thickness, del f. That particular del is effective concentration boundary layer thickness. You see, this is the del. From this analysis, it turns out that at the solid fluid interface, mass transfer is by molecular diffusion. Solid fluid interface, mass transfer by molecular diffusion. That solid fluid interface. In that case, again, let us come to either oxidation of coke or oxidation of metal, reduction of iron ore. In that case, one solid is there, another is fluid there. At the interface, mass transfer, whether it is oxidation of metal, reduction of iron oxide, or oxidation of carbon present with coke, here mass transfer is by molecular diffusion, even on fluid side. However, if we are moving away from the interface towards the bulk, convection contributes greater and greater share to the total mass transfer. Now we are coming to the segment number 4, that is mass transfer between two fluids. Mass transfer between two fluids. The reaction between two fluids is very commonly accounted in extraction and refining of metals and is exemplified by slag metal reactions, salt metal and gas metal reactions of various types. There are generally three theories of mass transfer between the two fluids. Hello, Sandeep.
Yes, sir.
Just for 1 minute, I'm taking a cup of tea. Again, I will come back to you.
Okay, sir.
Sir,
Just go 10 minutes ago. Again, I come back to you. Okay, thank you. Fluids very commonly accounted in extraction methodology, whether it is extraction, whether it is purification, refining. Generally, slag say metal and gas, or you can say carbon and gas, different fluids are there. In that case, there are three different theories. Film theory, boundary layer theory, or surface renewal theory. Film theory. Just like see, whenever we are considering reduction of iron ore, we are passing carbon monoxide. Carbon monoxide forms an envelope around the iron, a film form. Whenever you are to film and boundary theories, in previous reaction, at the solid fluid interface, the fluid layer sticks to the solid surface and hence is not renewed. That particular is not renewed. In such cases, film theory was first postulated by Nernst in 1892. According to him, the existence of a stagnant film of fluid adjacent to the solid surface, the mass transfer was presumed to take place by pure diffusion in the state film. That means in that case, you should penetrate that film, then only reacting fluid will go inside. That is by the process of diffusion. The thickness of the film is determined by hydrodynamics of fluid flow prevailing in the bulk of the fluid. This allows the attainment of a steady state thickness very rapidly, and since the film is stagnant, the diffusion is treated as steady state. Later on, Lewis and Whitman extended film theory to mass transfer between two fluids. At the time in the postulation, the existence of film on both sides of the surface, not on one side. The concept of film theory was later replaced by boundary layer. Then we are coming to surface renewal theory of fluid motion is possible at the interface of the two fluids, and hence the interfacial layers are capable of renewal. In that event, since an element of fluid stays at the interface for short element is unsteady, otherwise that is steady one. Important model of surface layer theories are Higby model and Dunquist model. According to Higby model, this is applicable for the flow at the interface is laminar flow. That means in case Higby, it's applicable to laminar, Dunquist, it is turbulent. This is applicable when the flow at the interface is laminar and is therefore free from eddies. Free from eddies. In that case, jumping mechanism and vacancy filling mechanism is not there because the laminar flow. Consider momentum transfer of two fluids, 1 and 2, and little bit calculation is there. That momentum flux at the interface is equal to minus mu 1 dv dx I1 x equal to 0 is equal to minus mu 2 dv 2 dx x equal to 0, where x equal to 0 to represent the interface. That at the interface, distance covered by at the interface, distance covered by the reactants at the product 0. At the interface, they are there. Now, in that case, generally, which comes to be dv double bar dx x equal to 0, dv single bar dx x equal to 0 is equal to mu I, mu double I. Supposing 2 is liquid and 1 is gas. If you reverse, 1 is gas, 1 is liquid, and 2 is gas. In that case, this should be mu double I divided by mu I. Now, in this case, mu 1 by mu double smaller than equal to 1, and therefore an approximation del I by dx for x equal to 0. That means x equal to 0, that indicates at the interface all the reactants as well as products are there. They're not covered. They have not covered any distance. They too. At the gas liquid interface, similarly, at the slag metal interface, slag would flow like a rigid body since it is much more viscous. Therefore, mass transfer would be by diffusion. Now, some assumptions of the Higby models are diffusion is unsteady since any particular liquid layer stays in contact with the gas for a short time only. The depth of the liquid layer is large enough to take the diffusion geometry as that of a semi-infinite specimen. All surface, dilation, and heat effects are negligible. Moreover, surface concentration is fixed. Now we are coming Dunquist model. According to this model, we have proposed another surface renewal model applicable to turbulent flow, according to which when turbulence exists at the interface, eddy packets move to and fro the interface at random and causes surface renewal. And eddy elements is thrown onto the surface, it stays for a while. It is waiting. Let another eddy come. You react together, give the product, and participate in interface mass transfer. And then is thrown back into the bulk. An individual eddy element may be considered as a rigid body for mass transfer purpose, and hence diffusion is assumed inside it. Also presume that this diffusion is of unsteady type. Then this introduces a term CS, which is the rate of production of phase surface per unit area per unit time. The chance of an element of surface being replaced by newer one is assumed to be independent of its age. Now, I have tried to cover as per the topic in these four segments. And every four segments has applications. Every four segments has applications. Now, any queries there? Please give me a mail or let us have a discussion for some time. We're having time. Sandeep, Yogendra, any participants?
Yes, sir. Yes, sir.
You see segment 1, mass transfer process and metallurgical kinetics. It's very big chapters, is it?
Yes, sir.
Convection transfer, mass from solid fluid, between the fluids, all these things are applications in process metallurgy, as well as any process, whether it is related to chemical or physical even. Please, any queries is there? Okay. Let me come to some application side even. You see, now mass transfer process and metallurgical kinetics. Let me take the reduction of iron ore, or let me take removal of sulfur, or let me take removal of any impurities present in pig iron steel making processes. Mass transfer process. Physical mass transfer, let me take chemical mass transfer. In physical mass transfer, simple thing, change in position. Blast furnace is there. But generally charged materials are iron ore, coke, flux. Even nowadays, we are injecting pulverized coke. Also, we are injecting pure oxygen, oxygen enriched air. All these things are there, but are located in different positions. And they are having the masses. Ultimately, either through the manually or through the machines, all these things in a calculated manner are brought to the furnace to reaction to carry out, are brought to the furnace. That means masses were there in a particular positions. They've covered a distance d. They're coming to the blast furnace, mechanical mass transfer, right? Now, once mechanical mass transfer there, we are maintaining the experimental parameter that chemical reactions will take place inside. Ultimately, metal and slag will form, and they will be separated. In this particular chemical reaction, iron ore is there, which is generally solid in nature. It is associated with different type of impurities, and it is based on counter current principle in the blast furnaces. Some portion of reduction is direct reduction, some are indirect. Direct reduction by means of carbon. Suppose carbon is there, iron ore is there. We have put together different places. Will they react together? They are not together. They will not react together. For the reaction to carry out, situation to be maintained, situation in terms of temperature, pressure, concentration. When it is maintained, what happens? Carbon contact with Fe2O3 off the surface of the iron ore and pick up oxygen from the iron ore, leaving deficient oxygen iron ore, either Fe2O3 to Fe3O4, oxygen deficient, Fe3O4 to FeO, oxygen deficient, FeO to Fe. That means in that case, gradually oxygen from the iron ore leaving the place, mass transfer taking place. That oxygen taken out by carbon in the form of mono or dioxide, and they escapes out. Just like visualize the first situations. At the interface, from one side, suppose both are fluid, both are in moving condition. From one side, one element is coming, one compound is coming, suppose Fe2O3 is coming. Another side, carbon is coming. They are meeting towards the interface. Then, at the interface, reaction is taking place. What active form? the product is not supposed to be present for a longer time at the interface, and that is to be taken out to buck up the metal side or slag side. In that case, main important thing is time, retention time of the product as well as the reaction at the interface. That should be as minimum as possible, so that the reaction area at the interface should be available for other reactants to participate. Now, suppose you are coming to the molten condition. Indirect reaction took place 30, 40, 50%. Then it is coming to molten conditions. Temperature is quite high. Again, reduction takes place. Ultimately, when gangue materials are separated from the molten metals on the basis of density difference, some of the impurities generally retained or picked up by metallic iron. In that case, those are to be removed. And that particular process of removal, we are coming to steel making, essentially a process of finishing process. When we are coming to steel making processes, even there, mass transfer is there. And generally, some of the elements, manganese, silicon, etc., retained. But in the metal phase, the elements are present as impurities. In slag phase, oxygen is there. Element coming from this side, oxygen coming from slag side, at the interface they are meeting together, forming respective oxides. These oxides again pass to the buck of the slag phase. The refining processes. Here the mass transfer is there. Maybe arc furnace, maybe induction furnace, maybe allowing there. In that case, generally, again, mass homogeneity is to be maintained. And for the homogeneity to maintain, we mentioned earlier, it should be by means of stirring. Stirring, mechanical stirring or chemical stirring. Mechanical stirring, stirrer are there, and the chemical stirring generally still making processes, lancing of oxygen is there at very high pressure. As a result of which, impurities oxidizes, and whatever the carbon present that oxidizes. But in that case, formation of carbon, what happens? Goes for incomplete combustions. You know, combustion of the carbon, two types. One is complete combustion, another is incomplete combustion. One is incomplete combustion, carbon monoxide. Complete comes the carbon dioxide. Sufficient amount of oxygen are provided. High temperature is quite high. You are providing sufficient amount of oxygen. Obviously, supposed to form carbon dioxide. That's fine. Carbon dioxide is formed. If carbon dioxide is formed, temperature is quite high. What will happen? Whenever you go for carbon oxygen diagram, it is seen that at high temperature carbon monoxide is stable. That particular carbon dioxide immediately will combine with another carbon present in the system to form carbon monoxide. In that case, the position of the carbon monoxide, oxygen are not fixed inside the bath. They're moving here and there. Random motions, they're moving here and there. What's moving here and there, mass transfer taking place. Stirring why are doing? Mass transfer at a considerable rate. Mass transfer at a considerable rate. That means, dear friends, whether it is solid fluid, whether it is fluid, whether it is solid gas, whether solid liquid, in every cases, mass transfer is very much important. Just to see, in case of corrosion event, is it a mass transfer process? It is a mass transfer process. Corrosion chemical reactions taking place, ultimately it forms some oxides or something like that. In that case also, mass transfer is there. The mass transfer is wide applications, and most of the processes may be physical mass transfer, may be chemical mass transfer. So dear friends, any queries there? Please raise questions. Again, the participants. Hello?
Yes, sir.
Questions are there?
Hello, sir.
How many number of participants are there?
24.
Any query? If not, I can leave. Or you can put questions in my mail, I can give the solutions in that.
Okay, sir. We are asking the participants to raise their hands for asking questions, sir.
Questions you can raise. Otherwise, you can send the questions in my mail, I can compile it.
Sir.
Quote a feasible above, which is feasible. I am there, I got to be no problem. If not, I have questions.
Dear participants, if anyone has any query, kindly raise their hands so we can unmute them.
Sandeep?
Yes, sir. I think there is no question, sir.
Okay, then many thanks to giving me the opportunity for the presentation.
Thank you.
Thank you, sir.
Shall I mute it?
Yes,
Okay
sir.
then.
Yes,
Thank,
sir. Yes, sir.
thank you.
Welcome, sir.
Jodi kichi hello?
Yes, sir.
एतार किसी नोट फोट किसी दबा के पड़े कि शॉर्ट टर्म कोर्स रे
Nice, sir. If any participant will ask, then we will contact
then you
you.
can tell me, no problem.
Okay, okay, sir.
Okay, thank you, sir.
Thank you so much, everyone. For the second technical session, Mr. Diptiranjan Behera is joining us shortly. Welcome back everyone. Now the time has come for our esteemed guest, Mr. Diptiranjan Behera sir, to deliver his talk. Mr. Diptiranjan Behera is a chemical engineer, passed out his BTech from SLIET Punjab and MTech from IIT Kharagpur, working in the petroleum division of Hindustan Petroleum Corporation, Vizag Refinery for last 10 years. Currently posted in Rajasthan Refinery, which is in commissioning stage as a process expert. He has been already worked as a production engineer in the SSAR oil Vadinari refinery for the period of 2 years from 2009 to 2010. He was working as a project fellowship in National Metallurgical Laboratory NML Jamshedpur for the period of 1 year from 2007 to 2008. He has also a key member in refinery safety policy, health policy and environmental policy decision making committee. So I request Mr. Diptiranjan Behera sir to deliver his talk. Please sir.
Now it is audible.
Yes, sir.
Hello.
Audible.
Okay. Okay. Very good morning to all of you, and a special thanks to Associate Professor Mr. P.K. Malik and Assistant Professor Mrs. Sonalata Behera and their entire teammate for inviting me as a speaker for this event organized by the Metallurgical Department of IIT Saran. So today the topic is ATF treatment section. ATF is nothing but it is a aviation turbine fuel generally used in the aircraft, and that may be a civil aviation, that may be a defense scenario. ATF is the generally fuel we are generally used for the aircraft purpose only, like in our domestically car, bikes, motorbikes, or any truck or bus, we are using generally petrol and diesel, but ATF is generally meant for the aircraft purpose only. So before that, we are going to the ATF section. We have to first know the what is the oil and gas scenario in entire India. So India is heavily dependent on the crude oil and LNG imports, with 82.8% import from different countries, and near about 45 to 46% of natural gas and LNG from all over the world. So that means we are entirely dependent on the foreign countries, which are generally meant to utilize for our requirements. So here the net foreign exchange outgo is 63.505 billion US dollar in the financial year of 2018 or 19 account of the crude oil imports. In India, we are generating near about 35.2 million tons of petroleum products from indigenous crude oil for production, whereas the consumption of the petroleum products requirement is 204.9. Means our generation is 35.2. That means our generation is around 20%, but our requirement is 100% required. So we are importing another 80% from the outsourcing of the crude oil from the different countries. So similarly, India is generated 31.7 billion cubic meter of natural gas locally against the consumption of the requirement is entirely double 46 to 48 BCM requirement, that is billion cubic meter requirement. So India is the second biggest importer of the crude oil and its products after China. That means China is the biggest importer of the oil. After that, India is the second biggest importer throughout the world. So though the oil resources are limited in India, so our entire dependency is on the outer countries. Again, the oil and gas scenario, what is our estimate is maybe it is triple near about 2025 to 2026 scenario. So as on 31st March of 2019, there are 23 crude oil refineries in India, of which 18 refineries are state-owned, 3 were privately owned, and 2 are joint ventures. Our requirement of 20 out of 23 crude oil refineries, 18 are state-owned. That maybe you know that IOCL, HPCL, BPCL, all are the state-owned oil companies, and 3 are privately owned: Reliance, this SR Oil, and another is Mittal Refineries in Bhatinda, and 2 are joint ventures. 2 are joint ventures means there is one is Bina Refinery in Madhya Pradesh, and another is Numaligarh Refinery in Assam. So the entire total refining capacity of India is near about 248 million metric ton, which is rising from 234 million metric ton from the previous year requirement. So day by day, 5 to 10%, we are adding our requirements. So refineries in India processed around 251.935 million metric ton of oil in 2018-19, achieving a total capability utilization of 106.6%, around 107%. So entirely our resources were utilized to sustain our requirements in the market. In the same time, we are a big donor of the economy package to the government of India in every year. With a total refining capacity of 69.2 million metric tons per year, the state-owned IOCL was the largest refinery in the country by capacity. So after that IOCL, our HPCL is the second in position. After that, BPCL is the third in position. So where the IOCL is generating 69.2 million metric tons per year, but this HPCL is, we are standing around 25 million metric tons per year, and the BPCL is standing around 16 million tons per year. So it's a huge requirement is there, though we are not sustaining our domestic purpose. So Reliance and this SR Oil are joined hands with us. So our in-country requirement is near about 80 to 90%. Only 10% requirements we are importing to the foreign nationals like Sri Lanka, Pakistan, Bangladesh, Myanmar, nearby our countries. So it is a big profit industry. So generally we are taking the crude from the other resources and we are refining it. We are taking the margin from there, then we are selling into the market. It is a win and win situation in the market. But there is a condition. There is a condition is the last 100 years is the coal scenario. The current 100 years is the oil scenario. Coming 100 years is coming the gas scenario, and after that maybe it is the renewable resources of the energy requirements are there. So totally we are now diversifying our business from oil to renewable source of the energy, oil to gas, gas to renewable source of energy. So HPCL is currently designing to sustain in the market. The requirement is 60 to 70% we are investing in oil, 10 to 15% we are investing in the gas, and 5 to 7% we are investing in the renewable source of energy. That may be the wind power, that may be solar power, that may be a tidal power. So slowly we are diversifying our media from conventional energy to the renewable source of the energy. Now you have to know basic things. What is the crude oil? Crude oil is nothing. It is generally impure oil generally found in the underground basins. It is called the reservoir, where the oil is stored underground in the Rocky Mountainous region. We are calling it is a storage, or we are calling it is a reservoir. In the reservoir, we are generally finding the gas and the oil. Gas is the lighter in nature, and oil is little bit heavier than the gas. So always wherever the reservoir oil is found in, the uppermost crust is dipped in the gaseous phase. So gas and oil, wherever in India we are finding, first is gas, then is the oil. But our prior requirement is the oil. So we never explore the gases, we only explore the oil to sustain the maximize the production of the oil from the crude reservoir. So here all over the world, the crude oil divided into two categories. One category is low sulfur crude oil, another is high sulfur crude oil. In low sulfur crude oil, it is having less sulfur content and the refining cost is minimum. Generally in low sulfur crude oil, having less sulfur content. But now it is the environmental protection is there are a number of numerous government standardizations are there. We are now running in Euro 6 standard. When we are talking about the Euro 6 standard, then we have to think about the sulfur content. When the sulfur content is maximized, then we are not withstand with the Euro 6 standard. So we have to withstand with the Euro 6 standard, we have to minimize the sulfur content in the crude oil. So to withstand with the guidelines of the Euro 6 standard, we have to minimize the sulfur content. In the similar fashion, we have to stand with the business also. If we are purchasing from the market low sulfur crude oil, then we have not to pay more money in the market, because low sulfur crude having less processing cost, but raw material cost is very high. To sustain in the market, we are generally purchasing the high sulfur crude oil. Generally, we are calling it as a Gulf oil, which is sulfur content is very, very high. So we are taking it from the different countries where the memorandum of understanding is there with the refineries, and the processing cost with high technology. We are segregating the sulfur with Euro 6 standards. Then we are selling into the market. It is a clear-cut business process. To sustain in the market, you have to stand with the guidelines of the government, and in the same way, you have to think your economic investment. How much your investment, how much your extract, how much you get the profit, and how much you are selling in the market. So it is clear-cut business. If you stand in the market, then you have to make a profit with better to better technology variants. So here, two types of the crude oils are there in the market. One is low sulfur crude oil, one is high sulfur crude oil. In high sulfur crude oil, the refining cost is maximum, and in low sulfur crude oil, refining cost is minimum. So low sulfur crude oil are generally found in Colombia, Venezuela, Canada, America. But in India, low sulfur crude oil are generally found in Mumbai High and KG basins. Here, high sulfur crude oil generally found in Gulf countries like Iraq, Iran, Saudi Arabia, Libya, Nigeria, and in India, it is found in Digboi and Naharkatia in Assam. So again, crude oil is coming from the reservoir. Again, it is segregated into two parts. One is offshore, one is onshore. If we are taking the crude oil extraction from the sea base, then it is called the offshore basin, which is in India, it is in Mumbai. And if we are telling it is a land-based excavation or land-based reservoir is there, which is generally in Naharkatika and Digboi, that is in Assam, it is called the onshore basin. So onshore basins are generally high sulfur contents are there. So whatever the found in Assam area, it is called the high sulfur crude, and which sulfur is near about 1000 to 1500 ppm of the sulfur. But in Mumbai High, whatever we are getting from the crude oil from the Mumbai High basin, is comparative to Assam, it is only 200 ppm. So when we are talking about the sulfur, then we have to come across to the treatment process to separation the sulfur to make it the standard of the Euro 6 standard. Euro 6 standard means minimum sulfur content. Why minimum sulfur content is required? Because sulfur is an ingredient which is pollute to the environment, which is pollute our health problem. It directly connect with our neurological syndrome problem, which is directly connected with the skin related problem. So as per the government guidelines, we have to minimize the sulfur content in petrol, diesel, LPG. You can say aviation turbine fuel, you can say it is a bitumen, wherever the fuel is using as a purpose of burning, there we can maintain the standard. That is called the Euro 6 standard. So like this is the crude oil scenario in the country, like our India. So like our India, 80% of the oil we are importing from the other countries. Only 20% of the resources. Currently, Government of India given another 36 license to our national and international basis to digging more and more oil to make it 20% to the 40%. It is the target is 2030 target, and Reliance is the biggest bidder. After that, HPCL is the biggest bidder in the country. So to sustain, to not to blackmail from the other countries, so we have to sustain ourselves, because now oil is a backbone of the country's economy. China today is sustaining economy because of cheaper oil. They are making the cheaper oil from the Nigeria, African countries, Myanmar. So like that, their political network, they're spreading and taking the different wells, and they occupy the wells, and they're sustaining their country's growth. A country's growth is directly related to the oil sector or energy sector. That may be a thermal sector, that may be a oil sector, that maybe it is a hydro sector, that may be a renewable source of energy sector. But nowadays, solid fuel like thermal power plants are banned by the government. Slowly, it will eradicate the things. Like NTPC is also nowadays to sustaining their energy requirements. They are slowly diverting to the thermal and nuclear energy. So to sustain in the market, we have to upgrade ourselves with the current situation and segments. So now it is the oil refinery, typical oil refinery conditions. Typical oil refinery conditions in a refinery crude oil transformed. In a refinery, crude oil transformed and refining into more useful products like LPG, petrol, diesel, kerosene, ATF, bitumen. These are the few products which are naturally required in our current market scenario. It is also day-to-day requirements of our daily life. Like we are somewhere we are going and we required bike or car or truck or bus. Any other transport mode of the transport is energy requirements is required there. So in day-to-day our kitchen also we are requiring LPG. So it is energy is a minimum requirement of our day-to-day daily life. Here when crude oil is coming to the refinery, it is going for the distillation purpose. Here in distillation, there are various types of the products are coming from the different temperature gradients. So here it is in a typical diagram, it is an overall view that having the distillation unit, what are the lighter components that are coming onto the top, and what are the heavier components that is settled on the bottom. So lighter components from carbon content, it depends upon the carbon content, C1, C2, C3, C4, C5, C6, C7 like that, it is coming to C17, C18, C20 like that. So lighter components like LPG is coming onto the top. Then the temperature difference is coming 85 to 185 degrees centigrade is coming the gasoline part. Then 185 to 350 degrees centigrade is coming naphtha. Naphtha is generally we are using in the fertilizer plants for cracking purpose. And this 350 to 450 is from kerosene or jet fuel. This when we are talking of the aviation turbine fuel is nothing but a kerosene, but it is a superior kerosene. When we are talking about the superior kerosene, then it is nothing but different, little bit different from the normal kerosene. Now, what is normal kerosene? What is superior kerosene? It is only difference. It is their plus point, is the pour point, is the ignition temperature. So like this, we are differentiating from kerosene to the superior kerosene. So at 350 to 450 degrees centigrade, normally our kerosene or superior kerosene we can get from the distillation column. After that, 450 to 650 in this temperature range, we are getting the diesel. And 650 to 1050 degrees Fahrenheit, we are getting the heavy gas oil. It is a heavy gas oil we are generally using for the industry boiler purpose, where the steam will generate. There we are using heavy gas oil. A little bit it is denser than the diesel, normal diesel. So we are telling it is a heavier gas oil. And above 1050 degrees centigrade, it is the residual fuel. After that, it is coming the bitumen. Bitumen generally we are using for the purpose of road making tars. It is nothing but a road making tars. Generally, pitch we are using from the solid part of thermal power plant. But now petroleum coke is more demand in road making purpose, tar purpose. So in refinery, main challenges are the material selection. What kind of the material we are using for equipment purpose, for pipeline purpose, for we can say commissioning and erection purpose, lines or angles. What kind of the material is we are using? Because generally 90% refinery throughout the world are based on the sea base. Why sea base is required? Now, sea base is required because easily water availability. When we are talking about the water, where the refinery will be there, huge amount of the water is required, and it is highly polluted industry. So generally, sea-based water we are taking, and we are again disposed as per the environmental protection law. Again, we are disposed by treatment in effluent treatment plant. Again, we have to dispose it in the sea. So the huge requirement of the water, it can only fulfill by the sea. So 90% refineries are generally based on the sea-based view. But like Mathura refinery or Mittal refinery or a Bina refinery, they are river based. They are taking the water from the river based. But 90% of the refinery is sea based because huge amount of the water requirements are there in the refinery plants. So when we are treating with the saline water, then chances of corrosiveness is increases. And because of the sea-based plant, corrosion atmosphere will be there. So we have to protect our equipment. We have to protect our pipelines. We have to protect our pumps. Whatever assets we have to protect it. So for that, when we are thinking about the protection, then again the thinking is coming about the cost. So from the cost and protection, so we are deciding, or the standard refinery is deciding to all the requirements has to be made by the carbon steel requirements. Now among the various classes of the steels, carbon steel is most used material for construction of petroleum refinery. Static equipments like pressure vessel, columns, boilers, heat exchangers, condensers or pipelines. The carbon steel is candidate material for concrete structure for withstanding the load of LPG, mounted bullets, or crude refining product, storage tanks, bottom supports or column and pressure vessel, 5 roof support structures. Almost 98% of the refinery equipment are constructed from different grades of carbon steel. So it is cheap, it is best. Life is also not more, we can say, like a stainless steel, but our requirement is fulfilled. If in high corrosive atmosphere, the carbon steel is the best, cheap and best material we can use. And after its life is over, we can recycle it. That is the main challenging things. After utilizing, we cannot throw it, we can recycle it, and it is as a scrap, we can sell it to the different steel plants, which is very high demandable things. The various advantage of using carbon steel in refinery equipment is very low cost. Corrosion resistance, less corrosion resistance, is easily available, easy to recycle, excellent weldability, oxidation resistance at intermediate temperatures. So these are the plus points, these are the advantages of carbon steel are generally using in the refinery scale of production. Here a typical tabulation is there, where the carbon steel for iron is 99.18 to 99.53, and carbon is varying from 0.08 to 0.13 percentage, and manganese 0.3 to 0.6, phosphorus is 0.040 maximum, and sulfur is 0.050 maximum. So this is the standardization of the material we are using. After knowing what is the energy requirement in the country, after knowing the crude oil system and regarding what kind of the materials we are using, now we are discussing about the aviation turbine fuel. Aviation turbine fuel is commonly known as the aviation turbine fuel is specialized by byproduct crude oil used to power the aircraft. Originally we are using to power the aircraft. And the primary function of aviation turbine fuel is to fuel an aircraft energy content and combustion quality. Other properties of the product are stability, lubricity, fluidity, volatility, non-corrosivity, and cleanliness. Moreover, it is requirement is highly cleanliness environment is required. So rather than the SKO, we are little bit treatment the SKO and make it the ATF, aviation turbine fuel. Fuel is also used as a coolant for certain fuel system components also. So this fuel is also used as a coolant in certain fuel system components. So today's environment, ATF is most demandable fuel of last decades. Last 10 years, it is the most demandable fluids, because as India is a developing nation, now it is going to be more developed. So requirement of the aviation turbine fluid is increases 10 folds. 10 folds. Now the current scenario, aviation turbine fuel cost is 45,000 per kiloliter. It is one of the profitable unit inside the any refinery in the India. So HPCL share in the ATF in the current scenario is 55%, where the IOCL is the biggest producer. Still it is in the second position, is the 42%, and rest is the BPCL. And Reliance, SR, and Mittal, they are selling it into the international market with the international prices. Now international prices is more than the Indian prices. So when we are talking about the ATF, the next thing comes into the mind, the sulfur. As we know that Euro 6 standard of petrol or diesel, the sulfur content has to be less than 10 ppm. Earlier, when the Euro 4 standard is there, the ppm content of the sulfur, it has to be less than 30 ppm. In petrol and diesel, it is less than 50 ppm. But now government standards improved, Euro 6 standards is less than 10 ppm both petrol and diesel, and in LPG it has to be less than 60 ppm, but in ATF it has to be less than 10 ppm or less than 15 ppm. So when we are talking about the content of the sulfur, but when we are taking the feed, that time high sulfur contents will be there, and after treatment the hello hello okay okay. When we are talking regarding this ATF, so we are talking about the Euro 6 standard, but Euro 6 standard is not applicable on the ATF. Euro 6 standard is only applicable to petrol, diesel, or LPG. Now in ATF, it is called the ASTM standard. It's the international standard. It has to be the less than 15 ppm requirements. But when we are taking the raw material from the upstream side, that is called crude distillation unit side, our ppm is 300 ppm. But when we are treatment it, when we treated it, then we have to make it less than 15 ppm, which is market requirement. This is not our requirement, it is a market requirement. To satisfy the customer, so we have to produce, and to satisfy the government guidelines, we have to produce within the restricted parameters, that is called the less than 15 ppm. So here we are discussing regarding this ATF treatment. So first is treatment objectives, then we are going for treatment methodology, then it is the process flow diagram, then we are going for the pre-treatment process, then we are talking about the fixed bed oxidation process, then we are talking about the post-treatment. So as we know, ATF is most profitable fuel for the refinery, and SKO is nothing but ATF. After treatment only it named as the ATF, and in this ATF section we are removed the RSH. RSH is nothing but the mercaptan, is nothing but it is a tertiary sulfur. Generally 3 types of the sulfurs are there in the crude feed. One is primary sulfur, one is secondary sulfur, one is tertiary sulfur. This RSH is a kind of thiol, that is SH group. Is nothing but a tertiary sulfur. We can segregate this, or we are differentiate the primary or secondary easily from the ATF, but we cannot separate it, the RSH from the ATF. So here our main objective is to remove it, RSH from 300 wet ppm level to it is less than 15 wet ppm basis. And more important is the freezing point. Freezing point, it has to be minus 47 degrees centigrade. Why freezing point is required minus 47 degrees centigrade? It is requirement is that when the flight or any aircraft, that may be a fighter aircraft or that may be a civil aviation purpose, it is moving in a high altitude area. When it is moving into the high altitude area, the temperature is drastically come down. It may be in the minus level. There are chances of the chances are that because of low temperature, maybe the oil freezes inside the engine, and maybe the ice formation will be takes place. And once the ice formation will takes place, the engine will be failure condition, and the accident will occur. Many times we heard this MiG flight will crashes in Punjab, the MiG 29-inch crashes in the Sonipat. Main cause is that fuel. Fuel is if not efficient, the engine failure is maximized. So always it is a strict guidelines, government guidelines. The freezing point must be below minus 47 degrees centigrade. Earlier we are standard is minus 37 degrees centigrade. But now in current technology, we can go minus 47. If further we also go minus 67 degrees centigrade, but we have to avoid by the market, which is minus 47 degrees centigrade. It must not below minus 46. It has to minus 47, minus 48, minus 14. In that range, it has to go. So now we're talking regarding the mercaptan. The overall formula of the mercaptans is RSH, and here R means the hydrocarbon chain, and mercaptans are the organic compounds of the hydrocarbons with sulfur. They also smell, a bad odor, and corrosive properties in the pipeline transport. So this is tertiary sulfur, which is called, we are the mercaptans. It is the organic compounds which is present in the hydrocarbons with sulfur, which is gives us the bad smell, and main demerit is it is a highly corrosive in nature. That means if we remove the mercaptan from the system, then two benefits are there. One is the smell will go, the odor will go, which is not affect our health, daily health basis. It will not pollute to the environment because of the sulfur. Another thing is that the engine part also we can say that it is highly corrosive in there. If we remove it, then we protect the engine, we protect the refinery equipments, we protect the refinery pipelines, we protect the pumps, and we protect the every equipment which is fitting this ATF in the refinery section to the retail section. So like that, we can minimize the cost, we can save the life cycle of the equipments, engines, related factors, but the storages are there. So therefore, if mercaptans are high in high concentration in ATF, if mercaptans are in high concentration in ATF, there must be to reduce the value of acceptable limit. Suppose it is showing that intake raw material, it is 300 ppm, but 300 ppm is not our acceptable limit. As per the government guidelines, it has to be acceptable limit is less than 15 ppm. So we have to convert it into the disulfide, which is less objectionable, and the value of ppm is giving us an acceptable range, that is called less than equal to 15 ppm. To separate the mercaptans from the ATF in the sweetening plant, normally the Marox is used. So Marox plant, it is generally this ATF sweetening system is established. So before sweetening, it is called the sour plant. After treatment, it is called the sweet product. Before it is sour, after it is sweet. After removing the sulfur, or after removing the thiol group, or after removing the phenol group, or after removing the naphthenic acid group. Now after removing all this, now it is called the sweet ATF. Some sour to sweet is happening in the Marox plant, which is called mercaptan oxidation reaction plant. Generally, this equilibrium distribution of mercaptans between caustic and hydrocarbon is unfavorable for long chain mercaptans, that they cannot be significantly used by the caustic. Generally, for this separation purpose, we have to use caustic as a chemical. When we can, after that, we can see how the reaction is taking place. So generally, caustic we are using to treatment from the sour caustic to the sweet caustic. Many of these mercaptans which resist extraction are soluble enough that do not enter into the caustic phase into the limited extent. So only to the extent of having the thiol enter into the caustic phase. So this is the thing happened in ATF section. In ATF treatment features, what are there? The mercaptans are organic sulfur compounds having the general formula of RSH. R is nothing but the hydrocarbon. SH is nothing but thiol group. Mercaptans are first oxidized into disulfide, and sweetening leaves the converted disulfides into the products. The sweetening process is generally used in the production of gasoline, ATF or diesel. This sweetening process is applicable to all, applicable to ATF, applicable to diesel, applicable to the gasoline production. What the catalyst used in diesel, in ATF and this gasoline are different catalysts we are using based upon the reaction condition. These mercaptans are nothing which is not susceptible to the Maersk extraction process. So for that we are using fixed bed catalyst sweetening process. This process is called a fixed bed. It is not a moving bed. It is a fixed bed catalyst sweetening process. Here in Maersk or mercaptan oxidation reduction process for ATF, there is no reduction of total sulfur. RSH is converted to RSSR. RSSR is less objectionable, but RSH is highly objectionable. So we have to convert it in disulfides, which is less objectionable and which is less than 15 ppm also. So in this process, there is no improvement in the color. So color is also a main factor in ATF. Generally, water color is plus 30, which is highly transparent and transparent, crystal clear. The color code is there. Every liquid having its own color code. So water is having a color code of plus 30, highly transparent and crystal clear. So making the standard to the water, ATF color is, it has to greater than equal to plus 15. If it is less than that, it indicates that impurities are there in the ATF, which is rejected by Government of India guidelines, because it is more prone to the accident of civil aviation sector. So the color must be above, greater than equal to plus 15. If it is above 20, then it is well and good. If it is below 20, it is also good, but it should be greater than equal to 15. In our President of India, their flight where they are using the color factor is the most mandatory factor whenever they are taking from any refinery or company. Their color factor is plus 25. It is highly impurity free. It is highly standardized specific content of the product. So there is no reduction in total sulfur. RSS is converted to RSS. In this process, there is no improvement in the color. In fact, some color loss is there to accelerate the oxidation of the precursors. ASF treatment depends on the endpoint, concentration of mercaptans, molecular, that may be a primary, secondary, tertiary, etc. Agents of catalyst poisoning or precursors, or etc. are for the reactor purpose. So it is a process flow diagram where the typical ATF unit is treating the ATF feed to the final product. It is called the sweetening of the ATF. So when we are receiving the ATF, so it is called sour feed. When we are producing the ATF after the treatment, it is called the sweet ATF. So here we see ATF feed. ATF feed is going to the electrostatic coalition, and there one caustic injection is there. So a little bit we have to light on this issue. ATF feedstock from CDUs may contain naphthenic acid. When we are taking from the ATF from the crude distillation unit, it may contain naphthenic acid, mercaptans and contaminants with H2S and water, which have several objectionable properties when present in a product and also interfere with treating operations. In generally, naphthenic acid must be reduced in a tolerable level prior to the treatment. So if acid content is there in the feed, that means it creates a highly corrosive nature inside the engine part. So first we have to treat or neutralize this acid and form a salt and make it is a spent and to separate from the feed. So for that we are using caustic as a base. So naphthenic is an acid, and to neutralize it we have to put caustic as a base. So acid plus base, it will neutralize and makes a salt, and it will settle on the bottom. And when it is heavier in the mass, then it is settled on the bottom, and the lighter component oil is going from the top of the coalyzer. So this is a typical process flow sheet of this pre-treatment section. Here the coalyzer is nothing but it is called a electrostatic coalyzer. In this coalyzer, a high voltage electric field around 32 kilovolt is maintained in the electrostatic precipitator. The dispersed droplets phase of caustic solution and hydrocarbon mixture passes to the high voltage electrical grid or fields. The mass contacting of naphthenic acid with caustic is carried out in the coalyzer electric field. The high voltage electric field causes the entrant droplets to coalesce and form larger droplets, which is eventually fall down by gravity separation method. This spent caustic is continuously withdrawn under the level control of 20% nearly 3 to 4 studs of the coalyzer. So main motive is that to separate the naphthenic acid. How to separate it? To inject the caustic. Caustic is a base, so acid plus base is neutralized, form the salt. Salt is heavier than the oil, it will settle on the bottom. The salt part is segregated on the bottom side, through it is a spent caustic, and the top fresh oil or fresh ATF without naphthenic acid is going for further treatment into the reactor side. So this is a reactor. After coalyzer, the air is mixing with the ATF, then it is going to the Marox reactor. So before mixing into the before it is going to the Marox reactor, air mixer is there where we are mixing the air. So why requirement of air is required? Air is nothing but the oxygen requirement. Here the RSH, whatever the RSH is there, in the bottom the reaction phase is there, and RSH is there. RSH is mixing with the oxygen. When RSH is mixing with the oxygen, it gives RSSR, and the hydrogen mixed with the oxygen makes a water droplets. It is highly exothermic reaction. To sustain this reaction, we have to use a fixed bed reactor. That is called the Marox reactor, where catalyst, caustic, and oil mix properly, and what are the naphthenic acid still present from the coalyzer, it will neutralize, and whatever the RSH is there in the reactor, it is reacted with oxygen, and it gives to RSSR. RSSR is nothing but the disulfide contents, which is less objectionable to the system, and water is evolved. It is called exothermic reaction. The temperature in the reactor zone, because of it is an exothermic reaction, so it will reach near about 65 to 70 degrees centigrade. When it will reach 65 to 70 degrees centigrade, it indicates that the water, whatever generated during the reaction, it comes into existence with the miscible phase. There are two types of the phases there. One is miscible phase, one is immiscible phase. So miscible phase you cannot separate out easily, but immiscible fluid you can separate out easily by density difference or by water wash. You can separate out, but miscible phase you cannot separate because of this 70 degree centigrade generated inside the reactor, and it is a highly alkaline zone because caustic is alkanized in the reactor base. So every reaction is occurred in the reactor, and the temperature zone evolved is near about 60 to 75 degree centigrade. And the catalyst we are using generally it is called Merox catalyst. It is a highly patent zone of the catalyst which we are taking from the America. Our bottle cost is around 40,000 to 50,000, and the recycle period of the catalyst is near about 3 to 4 years. So the ATF feed is coming from the top of the distributor of the reactor, and lower side, bottom side is the outlet, or it is called the collector side or the bottom drain speed. So generally inside the reaction main Merox reaction is taking place, and it gives us less than 15 ppm of product. Then the hydrocarbon flow along the dissolved air flow takes place from top to bottom. The pressure in the reactor is regulated by system back pressure control valve, and mercaptans are present in ATF feed stream. So activated charcoal are when we are talking about the fixed bed reactor, that it indicates that there is a fixed solid carrier. There is somehow it is a solid carrier for a Merox catalyst. What is the solid media of the carrier? That is called activated charcoal. Activated charcoal is to observe any traces of impurity constituents present in hydrocarbon such as phenols, naphthenic acids, basic nitrogen compounds. These trace of constituents likely to interfere mechanically with the performance of the catalyst. Caustic is continuously leached out from the bed and along with the trace of impurities. When the spent caustic color appears dark brown, it indicates that the reactor caustic is to be dumped and spent and charged with the fresh circulation of the caustic to keep saturated and the depleted catalyst bed. So here the reactor role is very much important because every reaction is feasible in the reactor zone. It is a fixed bed reactor, and the media of the bed is charcoal based with the catalyst of Merox catalyst. So here after that it is going to the caustic settler. Here number of steps are there. Here you can observe equipment wise function. First is the coalizer, it is the electrostatic coalizer. Naphthenic acid have to be removed. Next is the reactor. In reactor, it converts mercaptans into disulfides. Disulfides are less objectionable matter. Then the things is coming to the caustic settler. Here you see the after reactor, there is a caustic settler. In caustic settler, it is the removal of the caustic carried over caustic. So it is nothing but it is a simply it is an empty drum, but where space is that much large that whenever the feed is whenever the ATF is entered, what are the heavier things in the sense what are the caustic carryover is there during the realkanization process, it will be settled down on the bottom of the caustic settler. Why? Because caustic settler is nothing but a horizontal vessel designed to permit gravity separation of carried away aqueous caustic from the ATF stream. So the traces of caustic carried out with the stream from the reactor is settled down on the bottom of the caustic settler. So in this way we can separate out the caustic by gravity method from the ATF. So whatever the spent caustic is settled on the caustic settler, it will be drained out to the shear, and the fresh ATF is going further carried out to the water wash drum. Here we can observe that water wash drum. So removal of water wash drum is nothing but it is a removal. If any process of the caustic is further carry over with the ATF, then in water wash drum it is to be clear, or you can any traces of the caustic will be present in the ATF, it can be washed away. And the pH of the water must not be greater than the 10. If it is greater than the 10, it indicates that more carryover is caustic is going with the ATF. So it has to be pH must be less than 10. When it will reach 10, the entire water will be dumped and fresh water has to be pumped into the vessel. Before water wash drum, one exchanger is there. This is called the cooler. Cooler is called the ATF cooler. Very small equipment, but the role is very much important. What is ATF cooler? It is a cell and tube heat exchanger. Cell side we are putting ATF, and tube side we are putting water. So the temperature after coming from the reactor, it is as near about 65 to 70 degrees centigrade. When it is passes through the cooler, the temperature zone is dropped down to 35 to 40 degrees centigrade. What it indicates, if any immiscible liquids like water is carried along with the ATF, then it will be separated due to the temperature difference. It is called the phase separation. It's called the phase separation. So because of the temperature differences, the immiscible liquids present in the ATF, like water, it will be separated out. And when it is, whenever it is separated out from the ATF, that means more water traces or more moisture traces are inside the ATF are almost came down to the normal. Then that settled amount is now going to the water wash drum, which is called a post-treatment section. Post-treatment section, and it is washed away the content in the water wash drum. So in water wash drum, we are nothing, but we are generally using as a dim water. We are generally using dim water where the pH factor is normally 8, 7.5 to 8. And after pH reaching greater than the 10, then we have to dump it down to the shear and fresh water we are charging into the system. So the role of the water wash drum is very critical, and from there we can ensure that caustic and water is not carried over to the ATF side or adjacent turbine field side. Then after water wash down, then it is going to the rock salt filter side. Rock salt, it is nothing but simple salt. We are taking in a day-to-day basis salt is same thing, the same salt, but it is called a rock salt. In nature, generally 7 types of the salts are there and present in our earth. So rock salt is the top quality of this salt. In generally in Hindi or Odia, we are calling it is a Sandhab Lavan. It is coming from the Pakistan, Lahore side, and entire base of the Himalayan glacier, this rock salt generally found, and we are taking from there only. It is very cost effective salt, and but the role of rock salt is outstanding. Both salts are there. One is ocean based salt, whatever we are taking into the food. One is rock salt based salt. Salts are both same, they both are NaCl, but difference are that more mineral contents are present in the rock salt, less mineral content are present in the sea salt. Whenever we are talking about the rock salt, it is more hygroscopic in nature, but whenever talking about the ocean based salt, it is more hygroscopic in nature, more hydroscopic in nature. So in rock salt, generally moisture it will adsorb, but in ocean based salt, moisture generally absorb. So when we are talking about adsorption and absorption, both are looking almost same, but their method of separation is a different process. So when we're talking about the hygroscopic in nature and it is a adsorption with the separation, then rock salt is the best method applicable in the ATF. If small amount of the traces of the water still present in the ATF, the ATF is passes to the rock salt filter and entire amount of the moisture are adsorbed by the rock salt filter. Slowly, when the moisture level will be more, salt will be depleted and the spent uh, salt, whatever the liquid condition, it will be spent out, but fresh moisture free ATF is going out of the rock salt filter. It is kind of treatment to separate the moisture content minimum to minimum to improve our freezing point. So it is one of the method to separate the water content or moisture content from the rock salt filter. So this is regarding the rock salt. Then finally, we are talking about the finally we are talking about this clay filter. Clay filter is the nothing but is the last filter after rock salt filter is going to the last filter section. In clay filter section, we are used to improve the color and clarity by passing ATF to Fuller's earth removal the surfactants. So here last is nothing but the clay bed. Clay bed is nothing but it is a Fuller's earth clay. Generally, in filtration in our academic side, and we are studying regarding this Fuller's earth clay. Generally, it is using for the filtration purpose, and it is hygroscopic by nature. So it is used to remove all soluble surfactants, metal compounds, particulate matters, corrosion inhibitors or nitrogen compounds, and thus improves the color, clarity, thermal stability of the product. So the equipment is provided. Also we can bypass it, but we can normally through this because we have to go to the normal specification as per the government guidelines. So like this, after the and after this clay filter, whatever the final product is coming, that is called the ATF, which is we are calling it is a Euro 6 standard ATF, or we are calling the international standard guidelines ATF, which is having no impurities, thermal stability is very high, clarity is very high, and almost it is a selling product. When we are talking about the selling product, that means the rate of our product in the national and international market is at par. We are competitive with cell-like companies in international basis also, because our ATF, HPCL ATF, is highly demandable all over the world. But our market is generally 90% we are sustaining by giving our the market requirement, rest 10% we are importing to the as per the customer to customer basis. So here the quality compliance of the ATF. So when we are taking ATF, the RSH is less than 300 ppm. After it is entering to the inlet of the coalizer, the acid number is little bit high, and outlet it has to be minimized. Color is also greater than equal to 10, greater than equal to 15 ppm. Doctor test is negative. Silver strip corrosion. Silver strip corrosion means to know how the corrosivity of the ATF. So one silver strip corrosion test is there. It has to be in this limit. We must not have cross the limit. If we cross the limit, that it indicates that RSH content is more. So RSH content is the more means silver strip corrosion test will be failed. So after that RSH content, it has to be less than equal to 15 ppm. Freezing point is near less than equal to 47, and total sulfur is 0.245, and pH of 19 is equal to 10 ppm. So this is all about the ATF treatment process, which is carried out in the current situation in the HPCL refinery. So that's all. My talk is over.
Thank you so much, sir, for giving us a brief scenario on oil and gas, various equipments and its function. Thank you. Delegates who want to ask questions can ask. We have 15 minutes for discussion.
Yes, Assis, you can ask a question. Hello, Assis, it is audible to me? Hello?
Hello.
Yes.
Sir, I have a small question actually.
Okay.
Okay. Sir, I am Sujit Kumar Pradhan, Assistant Professor, Department of Civil Engineering.
Okay.
Actually, actually, I am working on a bitumen related material for road construction actually. As bitumen is the byproduct material. Actually, I have seen when we will construct bituminous concrete road or DBM road or anything type of road, physical properties is the primary thing, sir. So physical properties of the material means or of bitumen is primary thing. Okay, sir. So if from the last, I think in the year 2015 or 16, there was one criteria. The flash point of the bitumen was up to 190 degrees centigrade, sir. Right. Now the code has changed, and the flash point of the bitumen should be 220 degrees centigrade. Okay, sir. At that time, in the year 2015, when we tested the bitumen, that is 190, 195 is coming in the laboratory. Now, the code is changed to 220 degree, but when we are testing in present time, it is also coming 190 degree or less than that. So, if when the codes are preparing, 190, let the flash point change to 190 to 220 degree. Sir, in your plant or IOCL, is there any change in procedure or you are adding in bitumen something else? Or what is the scenario actually? Means code is changing, actually, but the laboratory testing are not coming. What is the scenario actually?
Actually, sir, this bitumen, earlier it is nobody care about the bitumen. But last decade, this bitumen was of the major source of money or a major source of profitability we are collecting from the market, from refinery end. So when we are refining the crude oil, if the crude oil quality is good, suppose in generally in India, 80% of the oil we are refining, it is a high sulfur based crude. When we are talking about the high sulfur, then bitumen is also quality is less quality comparative to low sulfur bitumen, sir.
Okay.
So that is the major criteria based on the raw material. So many times a company what is doing the guidelines, they are bypassing the guidelines because they have to, in the cheap cost they are taking to the material. They are producing the different grades of the fuel oil, but bitumen is the last priority grade, which is not demandable at all. But last 10 years, because of the high demand, they cannot change the raw material, they cannot change their profit. This is the additional profit a refinery got get. So what they're doing, two types of the things they're doing changes in the raw material. One is high sulfur, one is mixed sulfur. When the high sulfur grade is coming, there's a plus point is high. And when mixed sulfur is they're doing, the plus point is less. When they're mixing, it's called as average. So there is a standard and code of conducts are there, because people are less concerned, less care about this product. So simply without any guidelines, they're sending into the market. So there is guidelines, but they're bypassing the guidelines.
Means due to increasing demand, means this is sulfur content or any other
that
component.
Too, sir,
they are thinking actually about that.
That too, sir. Tar and pitch or bitumen, there are different sources are there. First source is coal-based source. First is coal-based, but coal-based now generally government is not encouraging that. Government is encouraging petroleum coke. Two types of the cokes are there. One is solid base, one is liquid base. But this liquid base coke is highly demandable because of the various standardization or characterizations of the fuel oils are there. Because more comparative to the solid fuel bitumen, and liquid fuel bitumen is high important or high demand in the market. So that's why many times we are bypassing the guidelines. So you people are facing problem for that.
Exactly, sir. No, still, if let there are 7 to 8 physical properties that there. Means the first point is not working, but other points are passing that criteria. That's why there is some safety factor like that. So accordingly, I think they are doing like that actually. But for research purpose, actually, this is creating problem. For heavy construction, there is no problem, sir. Huge construction, no problem. And for bitumen, sir, for bitumen property testing, for sir, dynamic ceoriometer. Just we are taking, sir, 1 ml of bitumen, just a drop. Means if their property is something a carbon or sulfur change, then the whole thing is changing. Whole thing is changing.
And moreover, the refineries is now the first seller to the market. It is the third seller to the market. That means we are selling, some third party is there to buy the product. They are again preparing as per the market standard and market profitability. Then they are sending you to the customer end. So we are not the first party. We are first party, but they are selling it to their third party. By third party, we can purchase it. Not directly, people are customer to us. So like HPCL,
I have seen also in our college or in IITs also, some parties are coming and they are submitting the bitumen and please provide us the report. We told why you require actually. This is IOCL or HPCL. They are giving. No, sir. Actually, we are purchasing from them, and we are doing some refinery works. Then and your certificate is required to purchase in the market actually. That is also criteria.
So Hindustan Petroleum now party with Hindustan Cola Limited is a French company. So we are collaborating with them. So whatever the bitumen we are producing, that SP32 or SP30 grade, where 2 grades we are making. So they are directly purchasing from us. After purchasing, they are doing something here and there, and they are selling into the market as per their criteria and sustainability in the market. And from their competitor also, they can earn more money from them. That is the criteria for them.
Exactly, sir. Okay. Thank you, sir. Thank you.
Thank you.
Thank you.
Okay.
Thank you, sir.
Okay.
Thank you very much for giving your most precious time. Thank you, sir.
Thank you.
So we have reached the end of today's program. I hope you have enjoyed this day. I must thank you all for your kind cooperation and I look forward to meeting you all here tomorrow. Thank you all.